Good afternoon, everybody. Today, we're going to talk about problem number 2 of the USACO 2022 December Platinum level contest. The problem is like this. You have a connected graph, is an unidirectional graph. Every time you're going to move some node from the graph, when you move the node from the graph, the connected nodes become the friends. So the question is, how many total new friends you're going to get? For example, in this case, right? So you have a graph like this. So you have 7 nodes and 6 connections. So you have node 1, which is connected to 3, connect to 4, and connect to 7, and 3 is connected to 2. 2 is connected to 4, and 3 is also connected to 5. So all those connected nodes, right, each node is a couple, is a friend, right? So 1 to 3 is a friend, 1 to 4 is a friend. So for example, if I remove this node, then all those are connected, right? Then 3 and 4 connected. This is a new pair. So it's a new friend. 3 and 7 are connected. That's a new friend. 4 and 7 are connected. That's a new friend. Then if I remove this node again, for example, then 5 and 4, they're connected, right? They become a friend. 5 and 7, they become a friend, right? So that's, then we have 5 new friendship, right, going on here. So now let's look at how do we solve this problem. Okay, remember the first problem we talked a couple of days ago? It's a graph. We said connected, right? So we said an easy way to count the number of edges is instead of starting from the original graph, which is all connected, we start from a graph that has no connection, and we add connections. So we will use a trick similar to that. But how do we use a trick like that? So the first thing, we're going to prove a theory. We're going to prove a lemma like this. If two points, U and V, will become, new friends, they will become new friends. They'll become new friend if and only if there is a path between U and V. All the nodes on this path, is less than the minimum of U and V. So that's the lemma we're going to prove first. So once we prove that lemma, then you can see we can just start from the smallest nodes. So how do I prove this? Let's suppose there is a path. Let's say there exists if there exists a path like this, right, from U to V, all the nodes in between are less than the minimum. Obviously, those nodes will be moved away, right, according to this problem, during some sequence before U and V are moved away. So then obviously UV are connected, so they are the become a new friend. On the other hand, if there is if on the other hand, if there is a W, if there's a node W that is not on the path, they are less than U and V. You can move that W away, but still does not impact this path, right? So it still works. Okay, on the flip side, let's say there is a point in there between this path, let's say X, which is bigger than the minimum of U and V. So that means at some point, let's say X is bigger than V, okay? At some point, V will be removed before X is removed, right? So it will not, U and V will not form a friend. So now we see this, that if U and V is a friend, if only if all the paths, there is a path between U and V, that all the node in between is on this path is less than U and V. Okay. So you will ask me, hey, how did I think about this? I'll tell you a bit later how did I think about this. So now, if we prove this theory, then this problem becomes very easy. Right? So I can start from counting from the smallest node first, right? Because to build this graph, I start from node 1. Okay, I start from node 1. It has a bunch of node connect to that, right? So those are the friends, right? Existing friends. Okay, now if I have node 2, then I start from next node, node 2. If node 2 and node 1 are not connected, then obviously, node 2 only have those friends. If node 2 and node 1 are connected, if you look at this path, right, then each of those nodes can be connected to any of those nodes. They become friends, right? Of course, if there is, but maybe some of the nodes are like duplicates, then you have to remove that. In another word, you are trying to merge those two sets, right? If you consider those as sets, basically what you do is just merge all those two sets together. Then you get, for example, you get another node 3. You can do the same thing, right? You can merge the set. Essentially, what you're doing is you're simply trying to do, for the adjacent nodes, you start from small to large, and you're trying to merge set, and you count. Every time you merge set, you count how many new things happened. Right? In this case, it's this plus this minus all the things inside it. The only thing you need to care about is when you merge sets, remember to merge sets, you need to do small to large, right? In order to do the log n merge. This is in the, remember in the USACO guide, in the Platon level, we talked about small to large merge, right? The way to merge two sets effectively, that was the way, right? If you have two sets, right, you merge the small one to the large one, right? Swap is of one and set merge is of n, right? So this is, each merge is log n, and then you have n of them from 1 to n, right? So the overall complexity is O(n) log n. So if we look at the official solution, it uses the same thinking as what I just described, right? So you start from the smallest to the biggest, right? So you do a small to large merge, right? And then you count how many, right? You count how many of these new things that is happening, right? So that is the solution. The coding is pretty simple as long as you figure out, you can use this algorithm, right? You start from small to large, and you figured out it's the way to do this is if only if there's a path, there's a path between U and the V, and all the nodes on this path is less than the minimum of U and V. Now you ask me, how do I know this? There is actually an algorithm. If you know this algorithm, you can actually look at this. This is very similar to what we did before, right? It is very similar to, think again, what is it? Yes, MST, right? Very similar to MST, right? Union find, right? Very similar to MST. There is an algorithm called word RAM algorithm. If you know how to do this, you can actually solve this problem in O(n) instead of O(n) log n. So the word RAM algorithm is here. There's a slide, there's a lecture, and I would like you to review this lecture after this class. That will be your homework, and try to code this instead of using the official solution for O(n) log n. Try to code it in O(n) complexity. The word-branch algorithm is from Professor Donald Knuth from Stanford University. It's actually a very famous professor at Stanford. And there's a there's a book called Art of Computer Programming. And if you read this, it is the word-rank algorithm is in his book. Okay, so or you can just go through this. Okay, so what is word-rank algorithm? It's, let me I give you a very brief introduction, and then I'd like you to go through the slides in details. So word-rank algorithm is like this, right? So if we have a tree, example of word-rank algorithm. Okay, if I have a binary tree, okay, if I want to say what is the LCA, right? we all know LCA can be done by log n, right? Complexity. Okay. The question is, can LCA be done by O of 1? The answer is yes. If the node are named this way. Let's say if you have a node 1, 3, 2, 4, let's say 5 is here, 7, 6, 7. That's probably very hard. But if the node, we always remember the Euler. If you look at the again going back, if you look remember the Euler graph, which is in the advanced, I believe. Eulerian tool, if you remember the Eulerian tool, if I can, for the binary, if I can node it like this, 0, 1, 2, if we'll just go through this and rename it, 3, 4, 5. I mean, this node does not exist, but I still name it 6, 7. I mean, this node does not exist. I'll still name it 8. Okay, so it's also very the same as when we did the segment tree, right? Then if you want to calculate, between 4 and 7, the LCA, there is a mathematical formula just to calculate that instead of doing the binary jump. For example, 7 to 5, there is a algorithm, like binary code to calculate that. So in this case, it's much harder simply because we named this way, right? Because by naming this way, we know each layer is to the power of 2 to the power of something, right? So we can easily calculate that. So for example, if you think about this is layer of 2, right? This is layer of 3. Obviously, their LCA is layer 1, right? So this and this, their LCA is layer 1. So this and this, right? They have an offset, so it's layer of 0. So that's one of the hint of how the word rank algorithm works. So the homework is to go through the slides of the word rank algorithm and then figure out how to use that to solve this problem. Very same approach, right? Basically use LSM with LCA to achieve O of n instead of the official O n log n. That's a challenge for the new year. Okay. I hope you guys had fun for the new year and have fun study this new algorithm. Then in the next class, we will talk about problem number 3. Happy New Year.